Our third example involves a beam or a bar that itself is at an angle. And so that, along with the tension force, which is going to be at an angle, is going to add a little more complexity to the problem. Make sure that your picture is nice and big so that you can really see everything in there. You can label things. You can really work with that diagram as you go through the steps of the problem. First thing we'll do is to label all the forces on the beam. There's going to be a weight force right at the center of the beam, just like we always assume. And then tension points along the rope. Now, tension pulls away from the wall as well, sort of down and to the right, but we are not interested in any sort of rotation of the wall. It is the beam that is the focus of our problem. So make sure that you're drawing the tension only on the side where it pulls on the beam. And then based on the way the problem is written, we are interested in a horizontal and a vertical component of the hinge. And so I take my best guess as to the direction of those forces and keep going here. So in order to take a look at the forces and to think about up equals down, left equals right, I'm going to need to rethink that tension force in terms of its components. And so I'll go ahead and put in the components, use dotted lines to represent those, and then that angle then between horizontal and the rope, that's an important angle for the next step here. So let's take a minute and look at our diagram. There's a number of ways that we can see this, but certainly there is a sort of a large right triangle that's almost completely formed here, where the 30 degrees on top, and then our angle would have to be the 60 degrees down at the bottom. So the angle that we're going to be working with is 60 degrees. And again, the 20 that's in the picture, it will be important later, but not in terms of the x and y components of our forces. If we look in the x direction, we can see that the horizontal component of the hinge force, F of h, is going to have to exactly equal the horizontal component of the tension. So T times the cosine of 60 will equal the F sub h that I've labeled here. Something else then that we can look at is the y direction. And so in this case, we can say that the vertical components of our various forces, the F sub v and the T sine of 60, together will have to equal 160. So it's always good to jot these formulas down. They're often used for a later part of a problem. If you're only asked about tension, you don't really need to write them down, but if there's something more that you'll be asked to do in the problem, we may as well get it all organized. So our next step then is going to be to begin looking at the tension forces, or rather the torque that are going to be acting on the beam. So we're going to use the tension force within that. We want to make sure the tension force is within that equation so that we can determine a value for T and then find our other unknowns as well. So we need to have a pivot point, a hypothetical hinge, and a good spot for that is going to be right at the hinge. In fact, in almost all cases, when there's a hinge in the picture, you're going to use that as your reference or your axis. So what I'm interested then is how is it possible that 160 newtons pulling down can balance this tension force that's basically pulling up and a little bit to the left. And the reason why they can balance is not because of the forces themselves being equal, but because the torques that those forces cause are equal. So let's start with the weight force. We'll think about, or we need to know, how far that weight force is acting compared to our pivot. And then we'll also need to know how big of an angle there is between the bar and the weight force. Finding that angle that's drawn in black here is going to find the component, or help us find the component of that 160 that points perpendicular to the beam. And of course, that is the only part that is really effective in making the beam try to rotate. To find that black angle, it might be helpful to find this angle instead. So you can see that the blue and the black angles, they are equal to each other. They are alternate and exterior angles or interior angles. Can't remember my geometry terms, but if we take a look at the triangle itself, 30 plus 20 is 50. Taken from 180 gives us that 130. So the way we're going to calculate that first value of torque is to say that the 160 Newton force acts 0.6 meters from our hinge, that times 160, and then times the sine of 130. And again, the sine of 130 is going to only take the portion of 160 newtons that is perpendicular to the beam. This then needs to equal the torque due to the other force, the tension force, and we'll have to go through sort of the same process. But of course, one of the nice things is that the angle is already given to us. The angle between the beam and the tension force is 20 degrees. And so we can say now that 1.2 meters, the full length of the beam, times my unknown tension, times the sine of 20, that equals the torque due to that force. And so these two torques need to balance out. That gives us a tension value of 179 newtons. And now that we have that value, we can very easily find our two components of the hinge force, just plugging them back into the original equations. So again, this is a good problem to study to make sure you understand how to pull angles, distances, and so forth from the picture, how sometimes we are using the angle with respect to horizontal, and sometimes we are using the angle with respect to the beam. It all depends on whether we are looking at the balance of forces or whether we're looking at the balance of torques.